Okay, thank you very much for the opportunity of giving this talk. And as you can see there, it's work I've done together with Smeenk. So while I give the talk, we will answer questions jointly. I'm a little bit out of breath because I run back and forth there. So hopefully that will get away. Okay. First of all, we've already talked a lot about string theory and about dualities. And what I want to emphasize in this talk is that we're not looking at the mathematical or the physical aspects of this at all, or not much at least. That is taken for granted. And we're not really kind of criticizing or evaluating that part of it. What we want to do is kind of put the philosophical and conceptual parts into focus and look at that. So since the math and the physics has already been done a long time ago, what I think is new is kind of this kind of philosophical gloss we put on it. And it might even be the case that these kind of way of thinking of dualities could be found implicit in the physics literature, at least to some extent, but it might not have been put in the forefront. And hopefully we'll think that this way of thinking of duality will kind of clarify some of the conceptual issues and things that we've debated here today. So, you would have seen, well, these kind of pictures are very common, right? And describing various dualities. You can have various string theories, and here also 11-dimensional supergravity. And there's this mysterious M theory, hopefully behind that, which we don't really understand yet. And often it's said that M theory is 11-dimensional due to this 11-dimensional limit. But perhaps it's better to say, I'm saying perhaps because we don't really understand M theory yet. And if you remember one of the questions that Amanda had of the list of these people from Springs 2014, one of those was, is there a description of M theory that doesn't really use space and time? So that's kind of an open option still. And as we've seen when we talk duality, the kind of prima facie pictures of different duals can be completely different. It can be different topology, geometry, which objects are seen as composite and elementary can differ, and all these kind of things. And there's certainly a value for calculational purposes to use both pictures. So we're not attacking the use of multiple pictures. For calculational purposes, it's perfectly good. However, from a philosophical point of view, we still get these conundrums. What's reality really like? Why? And these kind of things. And maybe physicists don't think about that as much or don't worry about it as much, but it tends to worry philosophers a little bit more, perhaps. And then, so let's look at this. Dualities, initial formulations. So dualities are transformations between theories such that they are distinct. For instance, strings propagating in different backgrounds, yet have the same physics. And here's the same quotation as from the previous talk, but the year isn't the same as that I just used.
The difference is that you're using the second edition,
yeah.
and he was using the first.
That's the only difference. Right. And here, I actually think that what he means, given to a question from the earlier talk, is I think it's probably better to say we have one system, but with one system with different descriptions by identical physics. But that could kind of be debated, of course, because that depends a little bit on the interpretation. Another one is from more about quantum field theory. There's two or more descriptions of the same theory, or in some cases, symmetry of quantum theory, which is not usually the symmetry of any classical limit. So that's another thing. And note that dualities appear also in quantum field theory. So they are not kind of exclusive to string theory in any way at all. And of course, ADS-CFT can be seen as a duality that relates quantum string theory and a certain kind of quantum field theory. But I'm not going to talk much about ADS-CFT at all. So two responses, like one natural response from the point of view of a philosopher, which kind of fits neatly in the traditional philosophy of science debate, is to think of this as underdetermination. It's basically, we have two empirically equivalent theories. They're distinct, and we don't really have any clear grounds for choosing between them, perhaps, but it's more or less that one is true or the other, but we can't know which, and maybe we don't care, or something like that. Another way of thinking, which I think is more common among physicists, is to think that there are actually descriptions of the same underlying reality. So it's just one underlying reality described very differently. That might lead us to think that not everything could be taken quite literally about what it says amongst concerning certain things. And this has also been discussed like invariant structure, people arguing for structural realism. I myself have touched upon this in an earlier paper, and other people like Ripples and David has also discussed that. But it's important now to think that there's some shared content. It doesn't have to be the whole mathematical structure, because that is obviously different, but there's a shared physical structure between these things. And other features such as space-time geometry and topology is kind of conventional in a way. And I would say that our view of thinking of this is more in line with the second option, more in line with the standard physicist way of thinking of this as being the same system described differently. However, we describe it slightly differently. So this is basically our response and our starting point for discussing this. And that is, in what sense are T1 and T2 physically interpreted theories? So these kind of theories that give different pictures, in which way are they physically interpreted? And what we're going to say is that those things that are identified as being dual are often, we would say, we can see them as mathematical scaffolding. They're kind of starting points of constructing a theory. Because string theory is a quantum theory, and that is the real theory, so to say. But to get there, for our ability to kind of reach that theory, we need to start somewhere. And that is what we mean by the mathematical scaffolding. So the dualities, we want to argue that they are caught in that scaffolding thing. And that will kind of change the way we think about dualities in certain ways. And so this is the outline. First I'm going to discuss dualities, and you've already heard a lot of this today, and so there will be no news, and we will not kind of go into explaining our scaffolding idea. That comes more in the second part when we discuss interpreting theories, and then finally some conclusions after that. So that's it. So let's look at elementary string theory. So once we try to figure something out with string theory, we often start with a classical theory. Of course, that's not the end point, but this is where we start. And at the classical level, we can think of a string moving through space-time, and that clearly forms a world sheet comparable to the world line of a particle. Here it's a sheet that can be kind of closed or open. And space-time is kind of the background in which this world sheet is embedded. We call it target space, because we will put into question whether we should always think of this as space-time in the end. But right now we can think of this. This is called a sigma model, often when you have this kind of mapping of one manifold into another, and then normally you quantize it and look what happens, stuff like that. So if this was just a classical thing, we would, of course, use the action, figure out equations of motion, and how would this string move through this space-time, and find everything would work out, nothing would be very strange. But of course, that is not the theory we're interested in. We're interested in the quantum. So when this thing is quantized, we find a lot of interesting things. Like a well-known example is that it requires a specific number of dimensions to work out nicely. Of course, there have been some work on non-critical string theory, but it leads to a lot of problems, so we can just leave that aside. But typically, you see, with a bosonic string, it kind of only works if you have 26 of these background dimensions. But bosonic string theory couldn't be used as a realistic theory, because it doesn't contain any fermions at all. So then we need superstrings, and there are many versions of superstrings, as you've seen in that picture in the beginning. And all of them needs target space to be 10-dimensional for the thing to work. And then, of course, to calculate everything, we do that in some certain way. We can figure out the spectrum by kind of doing some commutations, relations on certain things. But if we want to really fully understand it in terms of interactions and everything, standard way is doing kind of Feynman path intervals, but in terms of these tubes, and you have these different genus or genera, different genera of these kind of tubes that form all these kind of interactions corresponding to various Feynman diagrams. And it's can be quite complicated to calculate that, but that is what's done. So, and there are different kinds of dualities. And what we're going to focus on in this talk is target space duality. And I use target space duality to include all those things where there are dualities with respect to the target space. And the target space is, as you remember, what we at least prima facie think of as space-time in the various descriptions, right? And ordinary T-duality is the simplest version of that, but there are also mirror symmetries which are more complicated. But these dualities are kind of quite rigorously proven compared to some of the other ones. ADS-CFT has not been rigorously proven in general. It's kind of a strong conjecture, but it's not been rigorously proven to the same degree that these have. And we've already heard a lot of ADS-CFT, and that is not something I'm going to talk much about. Also with S-duality, we have these questions, what's composite, what's elementary, that kind of issue. And it might be interesting to think when our kind of idea of scaffolding, if that could also be generalized to address these issues about S-duality in ADS-CFT as well. Yeah?
Just one very small point. For T-duality, which mirror symmetry is a generalization of,
Yeah.
you can understand that as originating in worldsheet Hodge duality.
Yeah.
You take d alpha of x mu, and you contract it with epsilon alpha beta, and that makes you a dual field. So you can understand T-duality from the worldsheet as well.
Yeah. But that's kind of good because the T-duality is the ones that are with they have more like rigorous proof, and you can understand it in terms of worldsheet, and everything works out perfectly. Right?
Yeah. Mirror symmetry, very beautiful.
Yeah. So then let's look at T-duality, and this is the simplest example. And then we think of closed rings. Of course, this can be generalized to open strings and deep rings and stuff, but leave that aside. So we have one of those dimensions is compactified as a circle. And then energy and momentum modes, they are quantized due to these compact extra dimension. It's just having a compact space and you quantize that, in that you have these kind of restrictions. It would be the same with a particle. And then but you also have these winding modes when the string can wind many times around that. And it's quite easy to then, once you have the mass spectrum, which is kind of a formula like that, I'm now ignoring vibrational states. And then duality, it's easy to see that this is invariant under this exchange. So you exchange radius from like a bigger radius to a small radius, or vice versa. And the quantum number of these kind of moving around states and the winding states are also inverted. So you see they have exactly the same spectrum. Okay, fine. But we might still think, okay, they have the same mass spectrum, but what more? But it turns out that everything looks like quantized dual T-dual sigma theoretical equivalent. You can describe that you have this isomorphic Hilbert spaces. And if you have the kind of potential observables you can think of, there's a mapping preserving canonical commutation relations, equivalent partition functions, scattering amplitudes, everything. So it agrees on everything physically observable. And now, when I say physically observable here, it doesn't mean only what we, at present technology, can observe. It's like potentially everything physically observable, not just what we practically do. So that's quite amazing, right? But there's a conundrum. What is the radius of the compact dimension? And being a philosopher, one can still kind of feel, well, okay, we have all these potential observables being the same, but isn't this kind of a meaningful question or not? Maybe, maybe not. We'll come back to how we see this question when we come to the interpreting theories part. And another thing is mirror symmetry, which is a more general version of T-duality. And this little picture on the bottom there is just a two-dimensional slice through a Calabi-Yau manifold. But the important thing here is that here topology is different. And the exact definition of Calabi-Yau manifolds isn't relevant for the purposes of this talk. The only thing that is relevant is that there are mirror symmetries where the topology of the target space are different. So here we kind of think M4 is still a large 4 dimensions, and Calabi-Yau 1 and Calabi-Yau 2 are different Calabi-Yaus. And they are, of course, they of course have 6 real dimensions, or 3 complex dimensions, and they are described in terms of being three complex dimensional manifolds. And have certain nice properties. And why were people originally interested in looking at Calabi-Yau manifolds? That was because the aim was to kind of find out one way of getting some kind of realistic physics that we look like the standard model and behaves like our world. We wanted to find that. And early on, there was kind of good reasons to believe that, because people didn't know about that many Calabi-Yau manifolds and stuff. So now we know about many more Calabi-Yau manifolds, and there are also these kind of different ways of stabilizing them with fluxes and all that, and that leads to this landscape and blah, blah, blah. But I will not address that issue or that debate at all. I'm here just pointing out you have 2 different topologies, and the same thing happens. Nothing can be distinguished between these 2 cases. They have the same observable content in the same way as the ordinary TPRT. But then once again, you can be kind of the philosopher and all that, but what is the topology of space-time? What is it? And kind of ask this question and think, what's going on here? Is it a fact of the matter, or should we kind of discard this completely or not? And now, let's go to what we kind of think about this. So, interpreting theories. Forget about string theory now for a while and just think of this as in a more general setting. So, mathematical formalism, they can apply to a variety of physical systems, right? And one commonplace, or something everyone is aware of, is that certain equations, they appear in many, they are applicable for many different physical systems, right? So the wave equation appear, and you can use that to describe very different kind of waves, and you have other theoretical structures that appear and have completely different physical applications. This is just a triviality, just reminding you of this triviality. And this is kind of like the inverse of the duality. Here we have kind of same mathematics, different physical system. In the duality we have very different mathematics, but supposedly the same physics. So it's kind of a contrast, it's kind of like the inverse of it. But when we try to, so the point of saying this is basically just to say, if we just have a mathematical formalism, this is just an abstract mathematical formalism, we haven't interpreted the symbols in any way, it's not really physics yet. It's just an abstract mathematical structure, and that is fine. But we can use that to apply to different physical situations. So when we do that, we aim to get some kind of, at least schematic description of physical systems and see what in the mathematical formulas corresponds to the physical things. And sometimes when we have a new theory, to make sense of that, we kind of try to connect the new theory to the old theory in terms of limits or some assumptions about what in the new theory should correspond to what in the old theory. And this we do basically to specify the role, the physical content of what we're talking about. So saying this should be taken with like not too strictly or not too rigorously like some kind of dogmatic rule or anything. But it's roughly like this, that when connecting older, perhaps effective theory to newer, perhaps more fundamental theories, it's typical to think that the new theory has ontological priority. That just means that the new theory is supposed to be kind of a deeper or perhaps more fundamental theory that explains the old theory. But still, the old theory has some kind of semantic priority. because we understand the old theory better. We need to kind of see how does this new theory connect to the old theory? How do they kind of fit together? And that is kind of part of the semantic interpretation or the physical interpretation of this just purely abstract mathematical structure. And if we don't do that, we don't really have a physical theory. Of course, ideally we could just, if our physical theory is very concrete, we could identify certain things with things we directly observe. But when it becomes more and more abstract, it might be rather that we at least reduce it to, or connect it to the older theory, to give some kind of meaning to the thing. And we need that because mathematics is just mathematics. It doesn't wear its physical interpretation on its sleeve, right? So one example, when we think about, this is just from simple, basic, elementary quantum mechanics. So when we replace, when we look at the operators for momenta and positions, we have some quantization process with Poisson brackets and commutators and all that. And one correspondence we see recover classical theories, a limit, expectations, values, satisfy classical equations, Ehrenfest theorem, and all that, those kind of things. So we kind of see roughly. It doesn't mean that we have a complete understanding of all the details. It's not always necessary, but it kind of explains that a bit. But this does not always work, right? So ambiguities in quantization, limiting relations, gives us kind of an obstacle to interpretation. So it's different classical starting points leads to the same quantum theory. And traditionally, if we have, so that's probably on the next slide, right? So typically, when we have a classical theory that works well and is part of established science, and we kind of do quantize it some way, get a new theory, and then take the limits and try to get back where we started, then we kind of understand what's going on. But with dualities, we can't really do that to a certain extent, because the original classical formulations used to arrive at the quantum theory should not be taken as physically interpreted before. They are just kind of a starting point. And that means that the target spaces should not be thought to directly correspond to physical spacetime. They still play an integral part in the mathematics. They still play, we use them in the same way for every calculational purposes. But they should not think that they shouldn't be taken too seriously as like this is spacetime. So in the case of string theory, the quantum theory should somehow be the starting point for the interpretations. And the classical formulations can be thought of as scaffolding, something we kind of build up to get to the quantum theory. And they might still, of course, it's not that these scaffoldings are useless and we should kind of like, oh, don't use these classical scaffoldings. Because they are, of course, very useful for heuristic, pragmatic, calculational purposes. But we shouldn't just take them too seriously. We should be a little bit more wary about how we kind of physically interpret them. So that's what I'm saying. They can still give us clues about interpretation. So let us now look at where this lives. How do we recover space-time? If we think of space-time then as being something that we need to recover, we need to connect this deeper quantum theory to our more conventional or more traditional general relativity that we know and love. So the starting point must in principle be the quantum theory, but we will see how an identical spacetime appears in a classical limit. And then you could say this spacetime must be sufficiently uniquely specified by pseudo-Riemannian manifold. And this doesn't mean that the fundamental underlying description of spacetime is a pseudo-Riemannian manifold. It doesn't mean that at all. It just means that the underlying thing should be uniquely approximated by this thing. And sufficiently unique, I say that to cover modulo, diffeomorphism, and all that. Right? So what we at the mathematical level consider to be the same space-time at the classical level is still the same. Right? So roughly giving a specific solution or a specific case of string theory, what plays the role? This is kind of good. What plays the space-time role in this scenario? If it is assumed that it is the same underlying system we're looking at. So interpreting T-duality. So what is the real radius in the case of a T-duality? So these kind of originally are we use in the scaffolding. We can't prima facie take them completely literally. So we have to kind of say what looks like spacetime, what behaves like spacetime in this situation. And here it turns out that the large radius has a priority on the claim of being the right radius. Of course, you can use whatever starting point. You can use the small r or the big R to kind of construct the quantum theory. But it turns out this is Brandenberger and Waffa has done this a long time ago, and Haggett has a forthcoming paper on this from a philosophical point of view, where it's kind of pointed out that it will always look like the bigger radius, in a sense, because you can identify the state that represents the photon, and if you send it away in one direction, it will always kind of, in the relevant direction, it will always kind of be the large one that kind of looks like space-time. So I think even if we have both of those mathematical options, this is the one that kind of plays the space-time role to a certain extent. And for that reason, it should be considered to be the right radius. And this could also be there are some other arguments that are kind of perhaps a bit sloppier, but it's often said that T-duality shows that space-time has some kind of minimal length. And that kind of already there presupposes that the larger one is more kind of physically real.
Well, it's also not even true. I mean, actually, you can probe down to shorter distances in Calabi-Yau's.
Okay.
So that hand wave is actually just a hand wave. It's not
Okay.
really fully technically accurate.
Yeah.
There's also the issue, if you leave off the oscillators, you don't see one very important part about T-duality, which is that there are W bosons that become massless, and you give you an enhanced gauge symmetry at the self-dual point.
Okay.
There's an extra SU2 that comes about because states that have a winding number of 1 and some momentum are able to, they become massless, extra massless states in the spectrum at that self-dual point.
So the self-dual point, we have these extra symmetries and all extra.
Right.
Nice things. So, but would you still consider this point that what it kind of looks like to be the large to be real or
I'm
not?
not sure. I mean, the large one is the one that has a limit that gives us something familiar, like a big dimension of space-time. So in that sense, I would agree.
Okay.
I mean, but it is a duality, so everything at r less than the self-dual radius can be understood in terms of r greater than the self-dual radius.
Yeah.
So it's a little bit
sure.
fatuous to claim that one is more fundamental than the other.
Yeah, I mean, in terms of mathematics, we can use both.
Right.
But, so that is.
But you're saying there might be philosophical reasons to choose one.
Yeah. To think that the large one is that kind of plays the role of the familiar old
That's
traditional.
True. I would agree.
And interpreting mirror symmetry, in this case, it's difficult to do that. We have very different topologies. And here, I think one natural option would be to say that, okay, it's the 4 large dimensions. Well,
Can I understand the philosophical point? Are you saying that more familiar equals more fundamental?
not equals more fundamental. Not more
you
fundamental, but in terms of what thing we should interpret as
more
corresponding to
more
something.
familiar, indeed.
Yeah.
That's exactly the
It's a cheeky summary of the same point.
I agree.
Yeah, well, I think it's quite relevant. I mean, it's what it will kind of look like in this kind of. If we want to identify.
Like a space-time, indeed, it looks more like a space-time.
Yeah. Good. That's all.
We're used to big dimensions.
Yeah.
We're not used to small ones.
Yeah.
It's a statement about us, not about reality.
A little bit. I mean, to a certain extent, the point is that the two different dual formulations give us the same quantum theory, and then we try to identify what we should think of as spacetime, like what in this joint, either described like this or like that, should we consider to play the spacetime role, which we are familiar with. Otherwise, we could call it whatever, just some mathematical something. And that is why I have this idea that the semantic priority of the old theory is just to kind of connect the newer theory to the older. It doesn't mean that the fundamental description is like that. I said that earlier. Okay. So in the case of the Calabi-Yau, the large 4 dimensions, they're kind of the same on both sides, so they look okay. And it could be said that why should we, in this thing, I think it would be reasonable to refrain from giving a spatio-temporal interpretation to the 6 compact dimensions. They do not behave nicely enough according to these old-fashioned standard of approximating a familiar kind of space-time, right? So this is due to the ambiguity from the mirror symmetry. And certainly an interpretation of this is no problem if it is so that string theory or M theory at a deeper level don't have those kind of spatial-temporal things. It could basically be that these kind of situations is such that only the 4 big ones behave at what we traditionally think of as space-time. The other 6-dimensional, what's encoded there is the quantum content of like the relevant behavior there. So we shouldn't think of them having a spatial interpretation. It might be, and I'm not sure about that. I would be happy if someone would point out that it could be that in certain regimes, one of the mirror thing, if you kind of blow them up to macroscopic level, that one choice of parameters would actually look like one or the other. I don't know, but typically when we think of both of these as very, very small, and you only have the effective 4-dimensional dimension, I think that is what we should think of as only the 4-dimensional as space-time. But what happens if the clavia are not microscopic but kind of blown up? I don't really know what happens there.
Well, then you wouldn't end up getting a 4-dimensional world.
No.
You would get Kaluza-Klein corrections to the 4-dimensional physics,
Yeah.
which we would have seen already experimentally.
Hmm.
They have to be curled up really small,
Yeah.
because we haven't seen evidence, say, of extra dimensions opening up at the LHC
Yeah.
yet. We hope
Okay.
we might, but
Yeah.
might being
Might.
the key word.
Okay. So this is the thought. And okay. So summary here. Target spaces used to formulate string theory cannot straightforwardly be thought to describe spacetime. The resulting quantum theory must kind of be the starting point, even though we try to connect it to our old theory to kind of understand what we're saying. And the resulting quantum theory is, of course, the 2-dimensional quantum conformal field theory is kind of the important kind of building blocks to construct the string theory, quantum theory. And this is kind of the suggestion, in terms of suggestion of terminology, it can almost be seen as that, to only identify that thing which in a sufficiently unambiguous way could be represented by a pseudo-Riemannian manifold as an approximation, of course, deserves to be called spacetime. Of course, then people say, well, why don't you call everything spacetime? But I think that is kind of a useful conservative idea to kind of connect to. How does the new thing connect to the old thing? And if it doesn't behave enough like the old thing, why call it that, roughly? So it doesn't mean that the pseudo-Riemannian manifold that is unambiguous, roughly, is fundamental at all. There is a deeper fundamental thing that is not perhaps space-time. We should call it that something else, perhaps. So in 2-duality, the larger have kind of a priority just because that is kind of what looks like physics space. To be more, I mean, practically both of these would probably be extremely small. So it's kind of in a rather artificial situation when one is very big and the other is really small that we have to think about that. In the case of mirror symmetry, the 6 compact dimensions should not be given as spatial-temporal interpretation. They kind of encode this kind of non-spatial temporalness of the kind of underlying quantum theory, to some extent, I think. And this kind of also gets us away from this traditional way of thinking about duality, so it's like underdetermination. Is it this or is it that? It's like, well, look at the quantum theory, see what behaves as the classical thing. That's the real thing, and gives us a new way of thinking of dualities that is very different. It doesn't rehash the old conventionalism or Poincaré and all that. It becomes kind of a new thing. And further questions, to what extent is the scaffolding metaphor relevant for other dualities? So for instance, with S-duality, it could be that some kind of similar story could be done, but in terms of entities instead of space-time. And another thing is, what is this, and with ADS-CFT it's not rigorously proven, but if it was, maybe something else can be done there. I haven't really thought much about what that would mean. So, but it could be the case that if a purported duality is only approximate, this way of reasoning would probably not work. Then it could be argued in another way that one is the more right and more correct or more fundamental than the other, because the duality is not a strict duality, it's just an approximation. But that you have to figure out at a case-by-case basis, and then kind of the general philosophy works again. What does this tell us about the emergence of space-time? So if you think of the classical pictures as the dual things, like you have this classical picture and this classical picture, this way of thinking, if you have this scaffolding metaphor, we shouldn't think of this as emergence from this to this, or from this to this. It kind of destroys that option. It means that these are just starting points to get into the same theory, which in turn is given an interpretation. And to that extent, we could talk about emergence from the resulting quantum theory, but not in terms of from one original dual picture to the other. So that is the conclusion. And that was all, and here are some references. Thank you.
Thank you very much for that. So, my feeling is that the scaffolding metaphor that we're sort of using, so you talked about whether this story could sort of generalize or not, and so I don't know enough about these sort of space-time, these sort of dualities and all sort of space-time essentially, and how the story goes for those, but when you think about S-dualities, I'm sort of skeptical that the story would work there, right? So here's the thought. So traditionally, if you're a realist about a theory, right, you should also be realist about its implications, right? And normally when you think of how that plays out in physics, you think of a theory and you think about how it looks in the limit. So for example, if you are realist about quantum field theory, then you should be realist about what happens in the h tends to 0 limit, i.e. that particles obey classical trajectories and so on and so forth, right? So you put on the blurry glasses, you don't see the quantum effects, you should be perfectly okay about being realist about those things. So it seems to me that that the kind of instrumentalism that the scaffolding metaphor sort of suggests is just not really available, or at least not in that context. Because the problem with S-dualities, of course, and the specific issues that they pose is that while we should be realist about limits, it seems to me if you're a realist about a theory, you should be realist about its limits. When you have dualities, there's more than one limit, or there's more than one way of taking the limit. Now, it's not clear that that's really a problem with S-dualities because these theories, I believe, are conformally invariant, so that if certain particles are fundamental, they will be fundamental in some. So we tend to take fundamentality of particles to map onto sort of how small the charge associated with them is. As the charges get larger, they'll get fatter, they'll get bigger, they'll get heavier, they'll start to kind of just functionally do all the sort of things that non-fundamental particles do. But in any given world, because it's conformally invariant, the value of those parameters, say one knowledge duality, either electrical charge or magnetic charge, it's just going to take that one value. So there's no ambiguity in any one world what's fundamental or not. So the point being, it seems to me that the scaffolding metaphor and that kind of operationalism is not appropriate to S-dualities. I'm not sure how appropriate it is here, but also that it's not a problem in the case of those.
Yeah, well, I would say that, I'm not sure if I follow everything here, but wouldn't it still be the case, first of all, I mean, the all of it is still conjecture, like duality. So it might be that certain things are not, if it's not completely rigorous. It might be different from this. It might be different. It might be different from this story. Another thing is that I still kind of understand it in this case that you have one formalism, and then which is first described classically, and then you have certain solitonic states understood classically, and then when this is treated as a full quantum theory, you get both these kind of particles, right? And then I would think that the dual description would be another formulation of the theory, which is also classical, but where the solitonic and the fundamental are exchanged.
Yeah.
I start from that, quantize it, get the same spectrum out, I think that's the same story as we have here.
But I don't think so, because when you go to the dual, in a strong, weak coupling duality, what was classical is now quantum. G
Okay,
goes to
yeah,
1 over
that
G.
is-
So you can't argue
Okay.
that classicality on one side leads to classicality on the other, because that crosses with the idea
Okay.
of the strong, weak duality. So the couplings get inverted when you exchange the monopoles and the electrons kind of idea.
Okay.
So there's the question about whether it's always going to be classical quantum, and it's not always the case that we're looking at two classical limits of
Absolutely, and if you have a
Yeah.
classical duality, then they are the same theory. Precisely
Okay.
the same.
But
Not
then-
even the same,
but
different
then-
descriptions of the same thing,
but
they have to
then-
be the same.
The question then is, what do you want to be a realist about? So in that kind of situation, I think you just want to say, well, the two theoretical descriptions you have, you still wouldn't want to take them both fully seriously as giving you a guide to what to be a realist about. And so in that sense, I think maybe, again, this is something that Keizo mentioned that we're thinking about further, how to think about the scaffolding metaphor in other kinds of cases. And it might not work out in exactly the same way for the weak, strong coupling. But I think we'd also want to be hesitant about reading either one of those as guiding your commitments to some ontology, right?
Yeah.
Could you put that back on again?
Oh, no, just okay.
It should.
Okay.
Wasn't on.
So
Password and speak.
What?
that was really the very last one, because you didn't quite get my title
Yes.
right. The point I wanted to make.
Yeah. Sorry about that.
I noticed it.
It's just to be not equal.
Yeah.
So there are points. The slide where there were points where I thought I agreed, and points where I thought we were disagreeing, and actually the slide where you put my name on was the one where I particularly thought I disagreed.
Okay.
So here's the way I think about it, and maybe it's just sort of orthogonal. I really think we should think, that's what the not equals means. We should really think about there being sort of two spaces going on here. So one is, I'll call it target space, is target space, and that's sort of a space in which these quantum strings are actually living. And what the duality shows is there's actually no fact of the matter about the radius of that target space. And so maybe there's something even deeper underneath where you can sort of say, you sort of lose the duality, you can quotient out the duality or something, but at the moment all we've got is that there's this target space and there's no fact of the matter about its radius. But then there's this other thing which I call, the phenomenal space or space in the Tygol, which is absolutely, definitely big. It's a classical GR space and it's big. I can stretch my arms out this far. I can send photons around in the, Brandenburger and Bath way. And so they're really sort of so I cut things up sort of differently. I really don't want to say either of the target space radii, one of them is the right one. That's just something else. And then there's the phenomenal space, which I totally agree and sort of gets derived, but from that,
It's
the
kind of,
Brandenburger
it might
back
be
away
that
from the
it's
ambiguous.
misleading. I think that what we're saying is actually more or less the same as what you're saying, but preferring a slightly different terminology. It's kind of what you call phenomenal space is what I think we would prefer to call physical space, given this kind of idea about limiting to something. And that could be so then that's just a trivial terminological question.
So I'm happy with that. It just seems like it's actually at the level of the target space what you're thinking.
But
the picture
when I
of
say the large radius is the correct one, it doesn't really refer to a target space. It means that whatever it is, it will look like the big radius, regardless of what we use in the mathematical starting point. So I think we actually say that exactly the same thing. It's just a slightly different terminology with phenomenal versus physical, which could be just like choice of labels. And the other one is that it might be misleading when I say the larger one is the right one, because then it seems like I'm referring to the original target spaces. But the point of the whole thing was that those shouldn't be taken literally. So I actually think, as far as I understand it, we agree on that point. It's just a slightly different terminology or emphasis for it.
So then I don't understand what are you saying when you're sort of picking one of them? You can read the Brandenburger and Bath paper and you sort of operationalize what you mean by the size of the universe by sort of photonic I mean, then it's just a mathematical result. You excite the lowest kind of energy
But that's
quanta, and they're
because
going to.
you chose a probe. The choice
but
of probe
that's
is
right,
relevant
yes,
to the
yes,
question
yeah,
that you're
yeah.
asking. So if all you have is a photon, then you'll see physics of Kaluza-Klein
Right.
photons. If you have a string winding mode, you'll see other things, and if you have both, you could see these enhanced gauge symmetries. So I would say that if you're going to ask questions that involve operationalist anything, ask what kind of probes you have and
But
what
in-
you're
But that's the
using.
opposite.
But in
It's
general,
like the low
the-
energy ones.
Right. So
then it's
in
going to look
general, the
big.
approach would be put some probes in order to see what the space-time structure actually is in the theory that you have, right? So this is so.
It's
I think
one
your
of the
point that
ways.
it might be.
It's one
a
of the
bad
ways
probe.
that a physicist interrogates a spacetime
Right,
is to
exactly.
ask what probes can couple to it.
Right.
And you have to have a theory for how those probes interact with the spacetime.
Right,
So that's a
right.
prerequisite to being able to use the probes.
Right.
But when you derived, say, ADS CFT, they came along with the formalism. So you get a certain number of them, gravitons, open strings, closed strings,
Mm-hmm. Right.
etc. A certain number of Legos to play with.
Right. And
So
so,
it's
so what we're saying is partly that when you're trying to interpret the quantum theory you have, you're using probes like that. You're doing calculations to see how things behave, and that reveals what the space-time is in the theory. And it might not be either of the target spaces that you see. I mean, we don't think it's going to be a straightforward choice of one target space over another. It's going to be instead some story about, well, when you have a probe of this sort, what does that reveal about the topology or geometry of the space-time you're in?
I think that's the point. If you formulate everything in terms of probes in some operational way, and you are in the presence of a duality, then I don't see in what sense you would say that
One
one
set of
side
probes
of the
is
duality
more
is
fundamental.
space-time and
Right.
the other I don't know.
But I'm not saying.
Yeah, no, we're not
That's
saying
kind of
one.
That's
that's
not
kind
what
of
he's
more
saying.
point.
Yeah.
By
But it's not.
definition, they're going to be equivalent.
It's not that they're more fundamental, but it goes back to this point about semantic priority. As a matter of fact, the phenomena we're trying to capture are those of GR, and so the probes are low energy ones, and so it's always going to look big.
Right, and those are the light ones.
Right,
The
that's
light
what
probes to use
Yeah.
are always the ones that a physicist will put in their low energy effective Lagrangian, because the lightest modes are the ones that you are likely to be able to excite given your lack of your limited budget.
Right.
You only have a limited energy budget and you
Right,
can only
right.
excite a few modes, and
Right.
so that's why you focus on the lightest ones all the time. So you would probe with electrons rather than monopoles if the coupling was weak,
Right.
because those are the lightest modes in the system,
Right.
just because physicists always have limited energy budgets.
Right.
Let's just take one more question.
Yeah. Yeah, so I was, probably this is related to that idea, but on one of your slides, you don't need to put it back, but there was an idea that we have different meanings for different types of space-time, right? So we have to interpret them differently. And my question is, are you referring, probably this is related to mirror symmetry, but do you refer to something like the four dimensions are space-time in one sense and all the others are space-time in a different sense?
Yeah, well,
Like a lower, well, harder to probe and harder to
Yes.
intuit
Yes.
and less familiar. So there is like a gradient of space-time T's.
And I can tell you why. Because for even exciting the lowest mode in an extra dimension for a Kaluza-Klein particle, like a photon racing around the extra dimension, there's an energy toll that you have to pay to be able to make that excitation.
Which you don't pay in the four.
Right. Roughly speaking, you have to fit one de Broglie wavelength or two de Broglie wavelengths or three or four. That's why you get quantization of the KK momentum. That if you don't have them exactly, the wave function exactly coming back to itself after going around once, then it would sort of cancel itself out and you wouldn't have a wave function.
Right.
So the lowest mode, you have a 1 over R gap that you have to pay. So you can't excite extra-dimensional physics just a little bit. Roger Penrose made a mistake at Stephen Hawking's 60th birthday, claiming that all physics with extra-dimensional gravity theories were just wrong because you could arbitrarily excite a little bit of energy in each of those extra dimensions multiplied by the volume of the universe that collapses into a black hole. But he forgot that there's a Kaluza-Klein energy toll that you have to pay. And that will make a physical separation between your ability to probe the big dimensions
So
and the small
there's
dimensions.
like a non-democracy between the dimensions of space-time.
Right, because the probe has to pay different costs to go in different, the compact versus the non-compact directions. So for a physicist, there's an operational way to distinguish. But if you're going more philosophical, you might not want to be that simplistic.
But you still have different meanings that you associate to them.
Yeah, because I can do different things with my probe.
Okay, so let's address this question.